All right. Hello, everyone. I'm Trip Collins, and on behalf of the WISE Group and the WISE Zoominar Committee, I'd like to welcome you to another edition of the WISE Zoominar series. Today's theme is estimating the directional spectrum from incomplete information, and we'll be talking about things like the use of data adaptive methods. And there's some new and exciting progress in this area, and you're going to hear about it from our speakers. So first up, we have Daniel Zapata, excuse me, Zapata. And Daniel did his PhD between University Paris-Saclay and University College Dublin. He's currently a postdoc at ENS Paris-Saclay. His research focuses on in situ and remote wave measurements, upper ocean dynamics, and the role of ocean waves in renewable energy, climate systems, and marine ecosystems. And today he's going to talk to us about wavelet-based estimation of directional wave spectra from single point and spatially distributed measurements. Daniel, go ahead and share your screen if you don't mind. I think you're still muted. You're still muted.
Sorry, yeah, you
Oh,
still sharing, so you need to stop sharing for a while.
okay.
Okay. So, do you see my screen? It's correct. Okay, brilliant. So, thank you very much, Trip, for the presentation, and thank you, and all the organizers for inviting me. So, yeah, today I would like to talk about some of which was part of my PhD, which I finished 2 years ago, about the estimation of the directional wave spectrum based using a wavelet based method. So I'm sure that I don't have to convince you about the importance of the directional spectrum. We know that is one of the fundamental pieces of numerical wave models. For example, it provides an robust description, sorry, of the wave field in one specific location. You can distinguish the different components of the wave field, for example, different swell systems, the local growing wind sea, and you can separate, their own contributions. This is also important for wave breaking parameterization and consequently for RC interactions. I'll study on the effect of waves on the boundary layers and so on. However, the estimation of the directional spectrum is quite challenging. We will see why. The most important thing here is that we start writing the directional spectrum E, which is a function of frequency and direction, as the product of two functions. So one, which is the frequency spectrum, that's straightforward to compute. And the other one is the directional distribution function, D, which is the most difficult one. So everything boils down to compute the directional distribution function. What people have done is, well, traditionally, is expressing the directional distribution function as a Fourier expansion. So these parameters A n, B1 are the Fourier coefficients or the circular moments. However, for the case of if you have only one buoy, single point measurements, you only can have information up to n equals to 2, which is not suitable for complex sea states, for example. There have been developing more sophisticated methods like the family of the maximum entropy methods or the maximum likelihood methods. Basically, those methods try to find the best fit using different criteria like maximizing the likelihood or the entropy. But these methods not always are accurate and sometimes provide erratic results. Moreover, when dealing with limited data, and additionally, they require the time series, the recording time series to be stationary, which is not always true in the context of waves. So Mark Donnellan and colleagues in 1996 came up with a different approach. So instead of using the Fourier transform, they proposed using a wavelet transform. So when you have information in time, you can see the time evolution of your recording. You can detect the crest, the trough. You can preserve the extremes. However, you don't have information in frequency. On the other hand, when you go to the frequency side, you can find the peaks. You can see the distribution of energy across different frequencies, but you lose the information in time. So, for example, if there is some groups, some transient changes, some wind turning, so you lose all this information. So the proposal of or the idea of using wavelets is that you stay in the middle. So instead of going one side or the other, you stay in the middle and you have information on both frequency and time. So that's the role of the continuous wavelet transform. So the method proposed by Donnellan, which is the wavelet directional method, the WDM, so consists of imagine you have some waves traveling towards this direction, and you have an array of wave measurements. You can write the sea surface elevation as a combination of plane waves, something like this. And when you compute the continuous wavelet transform, you will decompose the signal into their frequency components or the evolution in time of those, of the wave energy. So you can see, for example, the appearance of wave groups, when they appear, what is the wave direction of associated to those wave groups. Um, you can see other stuff like, that when there are some reflected waves or contamination due to mirroring in case of buoys. You can see also the short waves changing direction. So that's pretty much what you can obtain using the wavelet directional method. But the objective is computing the directional spectrum. So the approach of Donnellan consists of writing for a pair of points. So you have 1 and 2, for example. You can write the surface elevation at any given time for a given frequency like this. So we can assume that the amplitude of the signal is statistically equivalent or the same in both points. So we can cancel out the amplitudes, and we end up with this expression in parentheses. Which we can write like this. So we know the phase, which is equivalent like this. So we know the phase because we are using the wavelets. So we know the phase in each point, and we can solve basically for k, because we also know the geometry, so the distances. So we solve for k, for the wave number vector, and with the wave number vector, we will have the evolution of the in time and frequency of the wave number vector, so we can calculate the wave direction as a function of frequency and time as well. Basically, the direction of the wave number vector, and counting, distributing those direction across each frequency component, we can have something like this, which is the final directional spectrum. This is just an example of one of the papers of Mark Donnellan in 1996. Okay, so that works for arrays, but it's true that we only, having arrays of measurements is quite difficult. It's not easy to deploy some, a spatial array of sensors. What we have usually is information in one single point. So we have GPS buoys, for example. More recently, there has been an increase in the use of these small buoys. We also have, the buoys that have been used traditionally by operational centers like NDVC and so on. So the meteorological buoys. And we have the ADCPs, for example. The case of the ADCP is special because we can have both one single point or an array. We will see later. So this is the kind of measurement we usually have. The question is, can we extend the WDM to work on single point measurements? So that's something we explore with some data collected by a Pocher buoy in off the west coast of Ireland. So we published these results in JTech a couple of years ago. Okay, so I will try to explain briefly how it works. So we use the fact that the waves are, the linear theory predicts the orbital motion. So we know that the surface elevation is in phase with the velocity. So for example, in a case like this one, so we know that if waves are traveling, all the waves are traveling towards the x-axis, the correlation between the u velocity and the surface elevation will be near 1. Whereas waves, the correlation of the perpendicular component of velocity and the surface elevation will be 0 at this exact case. So we use this and we leverage, the wavelet-based correlation, which reveals the covariant part between the surface elevation and the horizontal velocity. So we can write the correlation like this, and we can have an estimation as well, again, of the time frequency varying, let's say, wave direction as a function of the the ratio between the two correlations, the two wavelet coefficients, let's say. Okay, so we did a comparison of this wavelet based approach with different the classical methods. The first one is the direct Fourier transform method, which is the Fourier expansion I showed before. The maximum likelihood, the maximum entropy, and the Bayesian fractional method, I think, and also with some estimation of the Weierstrass tree. So you can see the estimation of the wavelet method is, can say, smooth, and you can distinguish, for example, per train of waves traveling, this direction, and shorter waves turning towards the wind direction. All methods predict the same, but for example, the maximum entropy also gives some say outliers or erratic estimation. Like for example, this which appears in all the methods, waves traveling backwards, which seems to be unrealistic, and it seems to be more like an artifact of the statistical fit. This kind of thing does not happen in the wavelet method. So another example, for example, here we are taking a time series of looks like this. So the TFS, which is the truncated Fourier series, same as I showed before. So it's predicting waves, the main waves traveling northeast, but at the same time, waves with the same direction, with the same frequency, traveling backwards. The estimation of maximum entropy is completely off. I mean, it's not even capturing the main wave direction. And the wavelet-based estimation is more, say, realistic in terms of what we can expect from a directional spectrum. Well, obviously, I'm showing only the the bad results of maximum entropy. Maximum entropies have been seen as one of the best methods to resolve the spectrum, but the problem is that it's not too stable. So it can give a very good estimation sometimes, but it's very sensitive to the data. Okay, so one of the trickiest part here is telling what is the ground truth. I mean, I'm comparing one method to the other, but there is no way to compare with some ground truth. So the closest we have to a ground truth is the circulant moments, or the directional spreading, which is computed from the observations the Boy observations using the cross spectral moments. So with a 1v1, we can compute the directional spreading sigma 1. And from the distribution obtained by each method, we can estimate also, the sigma one. So as you can see, maximum, the dashed line is the observed directional spreading. So the wavelet method and the maximum entropy method both are very close to what we expect from the observations, where in this case, wave watch 3 is a little bit well, completely off. It's not predicting quite well the observed spreading. And the maximum likelihood method is predicting, or is given overestimating the spreading. So again, the wavelet method is still within the what we expect, in terms of the spreading. So the problem, well, this is another kind of comparison. So in this case, I'm comparing with a parametric model. So again, the wavelet method. So in all cases, near the spectral peak, there are some differences. The maximum entropy method is the one which is closest to what is expected here, but the error bar, the size of the error bar is higher, telling us that this method fails sometimes. So there is a higher standard deviation. So the wavelet method appears to be the more stable and robust in this case. Okay, so we just built a Python toolkit called EWDM, extended wavelet directional method, trying to incorporate all these two methods, the original wavelet method and the one we are working on here. So it was published in Journal of Open Source Software last year or this year. So it's basically with a couple of lines of code, you can obtain a good estimation of the directional spectrum, provided you have the data. For example, here I'm using some methods to obtain the data from well-known sources like Spotter Buoy. It also works for CDIP dataset in real time, so you can obtain an additional estimation of the directional spectrum, and you can compare with those provided by them. It also works with the DCPs. For example, I was saying that a DCP can be seen as a single point triplet data because you have pressure, surface elevation, and the two velocity components. But it also, if you project the beams towards the surface, you can have like an array. We have an estimation of using the surface elevation and velocities in different depths, so there is not much difference. When we compare the triplet base with the array base, so we see that there is more noise in the array. It is because it is, the distribution, the size of the array is fixed, and there is not much variety in the distances. So it's difficult to predict or to obtain a good estimation for different wavelengths. Okay, so a little bit of work in progress. So in collaboration with Alexis Merigot and Roland Barthélémy from IFPEN, Roland is a PhD student in INS Paris-Saclay. So we are working on some experiments using LiDAR, so a LiDAR mounted on a drone. So we have some observations in the north of France. We computed the directional spectrum using an array of points. So extracted some 50 randomly distributed points. And the objective is to compare, the real directional spectrum from the source elevation with estimation, using when you have more limited data. We also have data from a nearby X-band radar, so that's another source of comparison. And that's it. So I will leave you with this, takeaway messages and future work. So thank you very much for your attention.
Excellent. Thank you, Daniel. If anyone has any questions, just go ahead and unmute yourself and ask while we're changing over speakers. We have time, I think, for just a couple questions before Zane begins his presentation. And Zane, if you're around, why don't you go ahead and load up your slides.
Yeah. I have a question.
Yeah, sure.
You hear me? I saw that you're doing the measurings with the drone and the lidar. What is the area coverage of the lidar?
Yeah, this radius of 20 meters around. For example, this one is 20 meters
Yeah.
of radius.
Okay.
It's a little bit problematic because you cannot capture longer waves. So if you compute the directional spectrum using the 3D Fourier transform, it will be restricted in wavelength, so for very short waves. That's why we have the X-band radar as well, so we can complete the information.
Yeah, interesting.
But the resolution is quite high, so you can focus on the short waves.
Yeah. Interesting.
Okay.
Thanks.
And we'll have time probably at the end of Zane's talk if anyone has a question for Daniel. Then I think he's going to stick around, so we'll have time to ask him then at the end. So if there are no further questions for Daniel, then I'll let Zane take the floor. So Zane Torres he's finishing up his PhD, and it was jointly administered by University of Melbourne and IIT Madras. Zane's title here is Transfer Function for Adaptive Methods of Estimating Directional Spectra Using a Fully Nonlinear Wave Model and Laboratory Measurements. Zane, the floor is yours.
Can you see my screen? Yeah. Yeah, can you guys see it?
Yes, sir.
All right, perfect. So yeah, I feel like my presentation is gonna be a bit more basic than Daniel's, but yeah, my name is Zane. Like Tripp said, I'm a PhD student with a joint degree between the University of Melbourne and IIT Madras. This is my final year, so hopefully yeah, I get to finish soon. Yeah, and I'll be talking about the transfer function. We set up this is part of my work, which was set up to set a transfer function for each of these adaptive methods that well, the most common ones that Daniel mentioned, WDM and MEM, and the maximal likelihood method. So yeah, we did this both numerically with a nonlinear wave model and with laboratory measurements. So yeah, the directional wave spectrum. Well, as we know, the directional wave spectrum is a diagram that we use to describe waves in the ocean, and it is very important since this diagram let us know how the waves behave, and so we can estimate how they evolve over time with the spectrum models. Using these models, we shape the spectrum by using the radiative transfer equations, which we have here, which shapes the spectrum according to the energy budget. So this includes the energy input from wind, the energy distribution with nonlinear effects, and dissipation by breaking waves and bottom friction, right? So as we know, these parameters are not perfect, so we assimilate them by correcting with measurements of the directional spectrum in the areas where we do have data available. So being able to measure the directional spectrum properly help us to know if we are parameterizing effectively in the models. How we measure them now is we can categorize them into two broad categories, which will be area-based measurements and point-based measurements. And now for the area-based measurements, we obtain them via remote sensors, right? Like satellites, radars, or cameras. But one of the main challenges with this approach is that the resolution of the measurements is either not that good, either spatial or in time. And that limits the accuracy when estimating the directional wave spectrum. On the other hand, if we take point-based measurements like buoys or arrays of staffs, we can obtain more reliable information in a fixed spot. But the challenge here is that the waves, well, they propagate in a two-dimensional plane, right? So having low area coverage makes estimating the direction of propagation challenging. So to overcome this, several methods for processing have been proposed. We have, like I mentioned before, and the ones that Daniel talked about a bit, is that we have the maximum likelihood method, maximum entropy method, and the wave directional method. We have other methods like the variation and convolution, but we'll focus on these three methods for this study, which are the most common ones used. The goal for us was to see how well these methods do in reproducing the directionality of waves. So let's talk a little bit about those methods, right? So these methods, we can separate them into two main categories, which is parametric methods that include the maximum likelihood method and the maximum entropy method. And then we also have non-parametric methods like the wave directional method. The main idea for the parametric methods, they're based on implementing a model that could describe the data that we are measuring. So for example, maximum likelihood method estimates the directional wave spectrum by fitting a statistical model that best matches the observed data. Similarly, the maximum entropy method relies on the model, but instead of focusing on the likelihood, it seeks for the spectrum that maximizes the entropy. That is the least biased distribution that still satisfies the data constraints. Now, on the other hand, for the wave directional method, instead of fitting a model to the data set, this one uses wavelet analysis to describe the signal and uses the phase difference between the phase difference and the geometry of the array to infer the direction. As we will see, these methods do not yield the same spectra and can differ considerably when estimating the directionality of waves. So how do we look at the directionality of waves? We jump into the frequency directional wave spectrum. So mathematically, we can express this the directional wave spectrum as a product of two functions, like we saw with Daniel, which is the 1D frequency spectrum times a spreading distribution function. The first one is going to tell us the amplitudes of the waves for each component for each frequency. And the second one is the one that tells us the direction of propagation of each component. We're gonna focus mainly on the second one, on this the spreading function. So yeah, this function basically tells us if the waves are propagating uniformly in a certain direction or if they're propagating over a broader range of directions. So different parametrizations have been proposed before to describe this behavior. For example, we have the cosine model by Longa-Higgins, and we also have the hyperbolic secant model by Donnellan. And here I'm showing a few examples of the spreading function with different spreading parameters. So if we consider the cosine model to the power of n, we can see that, for example, for higher numbers, the spreading is narrower, which means that the waves are more focused in direction. And for lower values, the spreading is broader, which means the waves are propagating at a broader wave source directions. So the thing is, when we use parametrizations like cosine and hyperbolic secant, we impose certain constraints on the shape of the spreading, which in real life scenarios, the shape does not always come as pretty as this, right? Like, for example, this one on the top is one taken from the ocean, and we can see that the shape is not as pretty. So to analyze the spreading, we use the spreading coefficient, which is basically the integral of these functions. So by integrating them, we get the energy that is being spread, and we don't have to worry about the shape of the spectrum. So same as with the values of n, if this spreading coefficient is high, then the spreading is narrower, which means more focused propagation distributions. And if it's broad, waves are propagating at a wider range of directions. So we did our analysis with this coefficient to check for the directionality of waves and how the method's doing propagating and in reproducing that spread, right? So that was the main objective for this part of the study. So we did this first. The first part was to use simulated sea surface for different sea states. We did this numerically, and we used Fourier analysis. Well, yeah, we estimated the spreading coefficient with the different methods, and then we proposed a transfer function we did this for different sea states. And then we went and did experiments in a laboratory setting and see if this same behavior was still followed in real waves, with real waves. So this is basically the workflow. So like I said before, we simulated the different sea states. We used the Fourier transform of the whole surface as our true spectrum. And that was our baseline to check how the methods did in estimating the spreading. That was the first part. The laboratory measurements, we did the same thing. We took some measurements from the surface elevation and see if the methods, maximal likelihood method, maximum entropy method, and the directional method were doing the same thing as the numerical analysis. So let's jump into for part one, the numerical analysis. For this part, we use the Shalikov model, which is a fully nonlinear model that simulates surface elevation of a wave field by solving the non-dimensional form of the principal 3D equations for potential waves. The model is made for long period simulations and includes energy balance by considering wave breaking damping and the spectral tail leak to create a quasi-stationary system. Wind forcing can also be included, but for our analysis, to not make things more complicated, we use no wind input. We generate different sea states, which we categorize by steepness and different spreadings. And combinations of these two parameters were made, which added up to 36 different cases analyzed. Since we're interested in the directionality, we looked into how the spreading coefficient evolved over time in the simulations. So we averaged the spreading coefficient for every steepness and separated them according to spreading, which are shown here at the bottom. So for example, for the broader spectrum, which is N1, that will be N1, and the narrower spectrum will be N4, which are also on the table. We can see that this is average on steepness for each one. So we can see that when considering broad spectrum, as the spectrum evolved, we didn't see any significant change, but we started to see more variation when we consider narrower spectrum. We saw a tendency of broadening that became more apparent, like we can see here, on N4 with our narrow spectrum. This leads us to believe that during developing seas, directionality tends to spread out if the initial propagation is too focused in direction. So what we did next is we looked into how each method performs in estimating the spectrum, the directional wave spectrum. So what we did is we extracted time series of surface elevation in different parts of the simulated surface, and we conducted first performance tests for choosing the right amount of points to use. So, well, these points that we used, they were distributed equally, spaced in a circumference with the same radius. So what we did is, to see the performance, we estimated the ratio of the spreading coefficient obtained from the adaptive method, and then with that, obtained with the Fourier analysis, with the Fourier spectra. So we averaged the estimations of all the cases with all the methods for each array. So the average, what we did for the performance test, we want this ratio. We came up with this expression. Since we're using the average, we also have the standard deviation. So what we want is this value to be as close as 0, meaning that the error or the yeah, the accuracy of all the methods are more aligned. So we ended up, we found that the 6-way prof was the best performing array for all of them. And this is the one that we chose for the analysis. Right, so after we set up the array geometry for the estimations, we looked into the spreading coefficient and how it changes across frequency. In this diagram here, I'm showing the normalized spreading coefficient against relative frequency, and this is the average of all the cases for each method. So we can see the narrowest part of the spectrum that was near the spectrum, near the peak frequency, and we saw broadening towards lower frequencies and towards higher frequencies. We saw sharp peaks for maximum entropy method and the maximum likelihood method, and the directional method purple aligned very well along peak frequency, but it deviated as we went into higher frequencies. In this range of higher frequencies, we saw that the maximum entropy method actually aligned more with the base spectrum. Just for reference, I added a couple of parametrizations made by Bowen in 1998, which sit a bit higher than our estimations. And this is mainly due because, well, these parametrizations were made on the reinforcing. We see that as the wind influence is less, the broadening rate was higher. Since R didn't have any wind input, our broadening rate sits way lower than the parameterized ones. Yeah, that's just as a reference. So next, to estimate the transfer function, we looked at the spreading coefficient, and this was done, the spreading coefficient at peak frequency. So at the top, I'm showing the ratio of the spreading coefficient with that of the Fourier analysis. And yeah, values lower than 1 means that the estimated spectra from the adaptive method is broader than the base spectrum, which was the case for the maximum likelihood method, which showed consistently broader spectrum. On the other hand, the maximum entropy method showed spectra that were consistently narrower, while the weighted directional method showed a bit more variation, but it was the average stayed closer to 1 than the other two methods. We can see the mean standard deviation here on the right on this box. And yeah, to obtain the transfer function, we plotted the spreading coefficient from the adapted method against the one obtained with the Fourier analysis. And then we just did a linear fit to see the tendency of each of the methods. With this fit, we found that WDM spectra were 3% narrower, MEM was 6% narrower, and MLM spectra was 14% broader. Yeah, so once we set up the transfer function, the second part was to see if this was also seen in real case scenarios with real waves. So what we did is, this part I did it in IIT Madras in India. So we used the wave basin they have there, which is a 30 by 30 meter wave tank with wave generators, which they have 52 modules in one side of the wave tank. And with those, we can program to generate different sea states we can get from a range of regular and irregular waves with different propagation distributions that can be simulated here. So we measure the surface using a pair of cameras and capacitance probes that were placed on a bridge right on top of the tank. The camera system was used to digitize the surface using stereo image processing. So same as the numerical analysis, we chose a pentagon-shaped array to be consistent. And we used the WISE model to process the image obtained from the cameras. We analyzed 16 different cases, which we classified as a combination of steepness and spreading that we have here on the table. And we gathered data for about 4 to 5 minutes. So yeah, using the probe measurements, we estimated the spreading coefficient with each of the methods. In this graph, I'm showing the mean spreading coefficient at peak frequency for WDM in purple, MEM in yellow, and MLM in red. These are averaged across all cases of steepness for each spreading case. This is with cosine to the power of 5, cosine to the power 15, and 20. We estimated the difference in the average there to obtain the efficiency of each of the methods in estimating the spreading, similar to what we did with the numerical approach. We found that in this case, WDM yielded a spectra which was 20% narrower than the theoretical input. Oh, here, I forgot to mention the stars here are the spreading obtained from the input that we put into to simulate the waves in the wave basin. So using that as our reference, we found that the wave directional method was 20% narrower, maximum entropy method was 9% narrower, and MLM was 2% broader. Yeah, so we saw the same tendency as the numerical results where both WDM and MEM were narrower and MLM showed narrower, broader spectrum, but the percentage weren't the same. For comparison, I have the percentages here for the numerical estimations. And although they weren't the same, it is important to know that it's still these percentages are still in the range when considering the error limits obtained from the transfer function, which we saw for WDM was a bit higher than the other two. So what we did next is we analyzed how different measuring techniques perform when estimating the directionality of waves. We used the digitized surface, measured with the cameras, and compared them to the estimations from the probe measurements. We extracted time series with the same geometry as the array used with the physical probes, and then we estimated the spectra using the different methods. In the diagram here, I showed two cases. On the left, we have the ratio of the spreading coefficient with the Fourier spectra for regular waves with steepness of 0.41, and on the right, for irregular waves with steepness of 0.124 and spreading of cosine to the power of 5. We can see the same tendency as before, like MLM broader, in both cases, MEM and WDM narrower. Here I show the estimations from the physical probes in red and the estimations from the digitized surface in blue. We can see a consistent higher value obtained with the physical probes, which means that the spectra obtained with the physical probes tended to be narrower than the ones obtained from the digitized surface. The difference was on average around 10% broader. The ones for the virtual probe in relation to the physical probes for MEM was 3% broader, and WDM was 9%. So this difference was mainly due to the fact that the cameras were placed adjacent to the wave propagation to reduce the light glares and the transparency of the water. And what happened is that this made the plane distortion along the axis of spreading a bit more significant when estimating the spreading. It's important to note, though, that even though we had the plane distortion error, the difference in estimation from the physical probes and the digitized surface was minimum, as we can see from these results. So finally, we looked into a real case scenario. This one was is from data obtained by the people from Inframer from stereo image measurements, and it's publicly available online. So we used the same approach in which we took virtual probes. We extracted time series from the surface elevation in a pentagon-shaped array, and then we estimated the spreading coefficient for 3 meters. We estimated the directional spectrum. we found for this analysis, maximum likelihood method was 12% broader, maximum entropy 1% broader, and WDM 8% broader. Even having those difference in percentage, the estimations are still consistent with the proposed transfer function within the error limits. But still, this was only one case, so it will be good to analyze more of these cases to see if this still holds. So just to finish up and conclude, the aim for this study was to see how the methods did in estimating the spectra, the directional spectra from point-based measurements, basically focusing on how they perform in reproducing the directionality of waves. We proposed a transfer function for each of the methods using Fourier spectra as our baseline. And from the numerical analysis, we found that the spectra estimated by MLM tended to yield spectra around 14% broader MEM, and WDM were 6 and 3 narrower than the baseline. And then we compared these results with estimations made in the wave basin from capacitance and video, and found that they were consistent with the proposed transfer function within the error limits. Furthermore, we compare the measuring methods and found that the orientation of the cameras when digitizing the surface is important, since slight errors might emerge if measurements are taken adjacent to the wave main propagation direction. So future work will include analyzing more real case, ocean case scenarios to see how the transfer function holds, and also analyze the performance under more complex conditions like wind force developing sea states. Ultimately, having an accurate estimation of the directional spectrum is a step closer to improving our spectral models for better forecasting and predictions. And that's all by my part. If you guys have any questions, I'm happy to take them.
All right, thank you so much, Zane. If there are questions, please just unmute yourself and go ahead and ask away. Zane, I think on my end, the slideshow got stuck on slide 17. I don't know if that was just me or if that happened.
Yeah.
It's catching up now, or I see a different slide now. I see 18, but we have a few minutes, so raise your hand or just jump into the conversation. And we also have Daniel still on hand, so you can also ask Daniel a question.
I have a question to Daniel.
Yeah, sure. Hi,
Please.
Daniel.
Yeah, this is Daniela.
Yeah.
You mentioned that the method that you propose, the extended wavelet method, I don't know the name. I don't remember the name exactly. You need to combine both elevation and velocity measurements. That's right?
Well, you can have three perpendicular components, either surface elevation, you can have the accelerations, the horizontal accelerations, the horizontal velocities, or the horizontal displacements, either of the three.
Okay, so you have this on the Sporter Boy?
Yes. So for the Sporter Boy, normally we have displacements. So it works with the displacements. It changes the transfer function, basically. So yeah.
No, but you mean both displacement and velocity?
No, only the vertical displacement and horizontal velocity or horizontal displacement.
Okay, so you just need the correlation between two displacements in that case. Okay,
Yes,
I didn't get this. Okay, thank you very much.
Yeah, sure. Thank you.
I was going to ask you, Daniel, or maybe just point out that you mentioned something interesting about the ADCP, that because the spatial array is so symmetric, it didn't provide a lot of unique baselines. And I noticed that when you created your I don't know what you call them, virtual probes in your 3D data. You used randomly spaced data, and that's probably a much better way to do it. I don't know. Do you mind commenting on that? You're on mute. I'm sorry.
I'm sorry. Yeah, you're right. Yeah, that's something we thought that maybe you know, having extracting some random points will improve the estimation instead of having a fixed length, because a fixed length will you know, make the estimation more, I don't know how to say. Yeah, it will have a fixed wavelength, so the estimation will be nice for the fixed wavelength, but for shorter wavelengths or larger wavelength, you won't have a good estimation. So that's what something we apparently, yeah, that worked because we have less noise in when we extract the random points.
All right. Well, if there are no further questions, I'll go ahead and bring this session to a close. I'd like to thank both of our speakers. I really appreciate it. Thank you, everyone, for joining. We'll see you for another WISE Zoominar series sometime next month. And be sure to check out our YouTube page where we post all of these recorded videos. So if you miss it, you can always check it there. All right. Thank you, everyone. Have a good morning or day or evening, wherever you are in the world. Appreciate you.
Thank you.
Thank you.